just a guidance, not any rules or anything. Don't think that you have to make these designs only. No, if you can make a more complex design, that is also fine. If you want to do some simple design, that is also fine. But make sure, even if it is simple, make a complete design, something like which is a like finished product kind of thing. Basically, what I am saying is, sometimes, I judge a lot of these programs worldwide, and what I see sometimes, people design only a single cell of a RAM, one cell of a RAM using 2T, 40, 60, or 10T technology, like 10 transistors and all those things, or only band gap reference, 2, 3 transistors, or very small design. So that is good for your learning or your maybe project in your college or research project. But we are looking something bigger, because we will be manufacturing a single RAM cell. It's not even like 2 3 micrometer by 2 3 micrometer. Like, it is very small. So we have like 10,000, 20,000 micrometer of space or more. If you make a design which is 1 micrometer square or 4 micrometer square, two micrometer by micrometer, and we have like 10,000 micrometer square micrometer area, like, it will be very small. Will not be able to accept those designs. Do not design anything which is very very small. But it could be good also, like band gap reference and all those things are good, but very small. Suppose if you are planning some analog designs, make it something bigger, add some digital part also, like that. But anyway, like, analog designs are little bit smaller, but choose something which has a significant amount of area, so that it can be manufacturable. For digital design also, if you are targeting something like very small, then it would be difficult. So if you say like, what is the maximum you can target, your design could be 100 micrometer by 150 micrometer. That is the kind of size we are looking for. It can be like 50% of that or 80% of that, or maybe like that. But don't make it like 10% of that. Don't make it like only one counter, only one adder, only one multiplier, like 16-bit multiplier, only one multiplier, which takes very small area. So that is the thing. But if you are designing like 64-bit multiplier, then it might take a little bit bigger area. Maybe we'll be able to accept. So that is the thing. Make it something bigger. And this is a example design, and we will send the, we'll tell you like what is the design, and how you can estimate your die, what could be your die area, how it can be estimated, like that. And the other thing I would say, after today, like, I'll be showing some example designs. Then I expect all of you to submit your design. So we'll send the notice also for submitting, and we'll be advertising in different social medias also. And just we'll create, we have already created, I think, the form, and there you can fill up your name of the design, and desk abstract, like what you are trying to do. That is must at the very beginning. then you try to do your design, and we'll have continue to have this kind of webinars, and we can discuss that what problems you are facing and all those things. And keep sending, also you can keep sending the Verilog file or spice file to us, so that we can give you feedback about like your design is very small, very large, or what is what, like that, whether it is going through our tape out things or that, like that. For analog design, last week we showed how to do the schematic as well as layout. You have to do the layout also. It is not that you will submit only the schematic. You have to at least make an attempt to do the layout. That is critical. For digital design also, you have to create, you have to make you make an attempt to create GDS, like whole tape out thing, and we will guide in that thing also. But at the beginning, like very first thing after today, what you have to do, you have to think what is your design that you are going to work. You have to send the design name, the title of your project, abstract of the project. Abstract means like 100 words or 200 words, like what your design does, what is the input output, what is the expectation, what is the outcome, like that, so that we can start deciding on the prices, and whether we should accept this or reject it, or we should give you some feedback. Definitely we'll give you some feedbacks, so that you can improve or do addition deletion from your project, like that. So this is the initial thing. We can start, I think, today's webinar with that thing, that introduction, and let people join as they come in. So, is there any questions so far from the first day till today? Just let me know. Okay. So I think my screen is visible. Today's topic is popular digital designs, and we will start with this protocol: Serial Peripheral Interface. Short form is SPI. So these pictures are just like actually just to present something. I have to present something that I have. That's why I have created this. But these are very well known. I'll show you how to do this. So go to any of the this thing. Go to your browser and browse to any what sorry open any tab, and like that you can see I am sharing my screen. Just type like SPI protocol. Those who are new, those who knows, I don't think they need any guidance. But those who are new and enthusiastic about doing something, This is just for them and not for experienced engineers. You already know what is SPI protocol. I'm just showing if you don't know and how to do. So basically, there will be a lot of specification, like lot of documentation, lot of training material, presentation all over internet. But how to get to the right thing? So generally, what I do, I open a tab and I just type like SPI protocol, and then I'll search it. Give me some time. It is coming up. See the first one, circuit basics, www.circuitbasics.com. You will see, you will get many such website. I find it very useful, circuitbasics.com. And I go there, I click on that, and it shows the working principle of a SPI protocol. So there are many other protocols in this site and also in other sites. So you can go to this kind of, you can search Google and find out the basics of this protocol. So I have taken some of the features from here, and I think it is taking some time. So I have compiled this in this presentation, and there you will get all the these documents, the pictures, how it looks like. So so SPI protocol stands for Serial Peripheral Interface. This is a very old protocol, and this is used to as it says, peripheral interface. Like with microprocessor, if you want to communicate with any devices that is there in the system, this is the way you can. One of the ways you can communicate. Let me share it again. I think I have lost the connection. Give me a time. I have lost the connection for the presentation. I'll connect it again. By that time, if you have any questions, let me know. Okay, I'm back, and I was trying to show this website. Um, um, so this is the website circuitbasics.com, and it shows like what is SPI protocol, what is how many pins it has, what is the protocol, like how the timing happening, what is the signal looks like, and many other things. What is the master slave configuration, like that. So the reason behind showing this website is this is not a specification. Generally, all the protocol specification comes in nice PDF format, and a nice PDF format, and it has lot of like jargons, some technical terminology or nice sentences which can be difficult to understand. If you go to any of these kind of website where they explain the things, it is much easier to understand. There are specification specs, standards are available in IEEE and all those things. Those are little bit difficult, and sometimes those as their official documents, they have all the complete specification, like all functionalities. Remember one more thing, there could be very nice to have features in all the protocols, all the designs, and there are some core features. So if you can complete the all the things, do it. If you cannot, at least make the core functionality of that design. That is the point I wanted to make. It is not that you have to do always the complicated and difficult things. No, simple things are also good, as long as the basic and core functionality of the protocol is implemented. So this kind of website helps it. So I have taken some of the examples from here, since I have to present something like that. Otherwise, you can find all of these all over internet. It is okay to take the take the examples from internet. It is also okay to follow their coding styles and all those things, but don't like copy like control V, control C, control V. That will not work, because everybody has their own way to code it. But ultimately, you have to make sure the functionality is achieved from your code. If you don't understand that Verilog code, even if you copy that, most probably you'll not be able to make it work. That is for sure. For sure, you if you do only control C, control V, it will not work. So it is okay to follow their code or take inspiration from their code, but ultimately you have to do by on your own, in your own hand, and you have to simulate. When you simulate, then you will know what is working, what is not. So serial peripheral interface, this is a very old protocol. Generally SD card, still today the SD cards are accessed by SPI protocol. There could be other, anything can be accessed, not an issue. But mostly later, earlier SPI used to be used for most of the other, like display, then communication, then SD card, then any other data transfer also used to be done by SPI. Later, more advanced protocols or other protocols were invented, and they started to use those newer protocols for other purposes. But still today, the SD card is accessed by a SPI protocol. So whenever you see a MP3 player, nowadays it is not there, but any music system, boombox, audio, any audio system will be is having that SoC is having SPI protocol. and also like Raspberry Pi or small microcontroller who accepts the SD card slot. They have camera. The nowadays camera is there inside the mobile, but standalone cameras, all the cameras will have SD card, and they are accessed by SPI protocol. So it could be this is a master and single slave that is there, but you have to design only one of them. So the specification is like only 1% or 2% changes between master and slave. You can design any of them. And the good thing is, if you are tricky in Verilog coding, a single module can be used as a master, and if you use some signal to turn it as a slave, that is also possible. That is tricky. So one module can be used as slave and master, but if you cannot make it work, you can either design master or slave. And it could be one master, multiple slaves. So for SPI protocol, multiple master, multiple slaves are not allowed by the specification. So only one master and multiple slaves are possible. So if you have multiple slaves, then you have to have multiple chip select signals from the masters. Then the pin count will increase. But if you want to make only one master which can access one slave, that is also fine, we'll accept it. But if you can make like my protocol can accept two slaves, three slaves, you can add pins. Okay, so that is fine. And whenever you are making this, first of all, go step by step. First, design one master with all which can accept one slave. Then, even if you are not submitting slave or not planning to work on slave, but you have to make a slave. Why? Because when you are testing your master, you need a slave also in your test bench, so that you can prove that from, yes, from master, if you this is the way you send the data and the slave can accept and decode the data. That proof you have to be you have to give us. Otherwise we'll not be able to understand whether your design works or not. So even if you're not submitting master or slave, so one master one slave is must for testing purpose also. So that is the thing. And SPI protocol has basically 4 pins. Three are almost fixed, like MOSI, MISO, SCLK. These three are fixed. Like MOSI means master out, slave in. Means in this pin, master sends the data to slave. And for a slave, this is the pin where the slave gets data from master. And MISO, master in, slave out, means slave sends the data to master using this pin. And for master, the same pin becomes like ulta, reverse. Here it accepts data from slave. So SCLK is always one way, the clock reference which comes from the master. Master gives the clock reference. Slave cannot give its clock. Slave has to follow the master clock always and accept or send data according to that clock only. So when a slave cannot send data like always whenever it wants, like if master wants, then only slave can send the data. And when master wants the data from a slave, then master will give the clock reference, and it will also give the chip select, the fourth pin, SS or CS. SS means slab select, CS means chip select. So when this chip select goes to this slave, goes down, then this slave is activated, and it can send data to the master. And also the clock reference is given. Based on that clock only it can send. Why the clock is needed? Because sending a data means generally there will be a register kind of thing, which register means a bunch of flip-flop, and it is connected as a shift register. And when you clock it, at each edge of the clock, the data comes out from that register. So that is the arrangement happens here. And so the clock reference is needed. So in the right side there is some like diagram. This is called generally timing diagram. So so when the SCLK means it is the giving the clock reference, master is giving clock reference to the slave. Then master is sending CS signal, means the slave is selected. Then master Mosey, in the Mosey pin, it is sending the data. And this data, it is a serial link, right? So this sampling happens at the rising edge or falling edge. That is up to you what to design. At that edge, it will be sampled. And when that edge of the clock comes, what is the value of that line of Mosey? That will be registered in the slave. Slave will also have a register, shift register. So it will accept data serially. It will be shifting and then shifting right. That's how it will accept the data. And there is some like conventions. Just read through the spec and gradually create that thing. So I will go to my SPI protocol, which is very simple. I'll show you how to. Let me see. Is this black window visible? The letters are visible.
Yes, they are visible.
Okay. Okay. So I have this directory SPI. See, this is how you can do. I'm not saying this is a recommendation, not a rule or something. You can do it anyway. So this is my design spi.v and test bench. So this is the test bench which test the SPI protocol. So if I open the SPI file, this is how it looks like. Um, uh, Code, and look at this code. Always at posage. This is the thing. So this is the heart of this Verilog file, the heart of the protocol. So posage clock in means this is the in like clock reference, and at a rising edge or reset. So data range, I have defined data range as like some register, 8-bit register, and if load data range equals to data in, and otherwise data range shifts left shift. So this is implementing a protocol. So I tried to make it as small as possible. So I have used very minimal coding, but you can do it like little bit bigger or like one by one, whatever way. So basically, what it says, this always block, any always block all generally will implement any sequential logic. So posage clock means it is going to like implement a flip-flop. So if it is 8-bit flip-flop, means this becomes a automatically becomes a shift register. And by this way, this operator double less than means each clock signal one is it is getting one left shift. So when you are getting left giving left shift, so data comes out from the MSB side of the register or something. If you want the data to come out from the LSB side of the register, then you have to give right shift. So adjust those thing little bit like carefully, then you will get this working. Again, this is a recommendation and guidance kind of thing, but you are free to do in any way it is possible. So and see, there is another thing. So if you see, uh, I told that this is only a this thing 4-pin protocol, but see how many pins I have in my SPI protocol. So one is like Mizo or Mozi is there, SCLK there, and SS. So SS in, SS in out. So I have used both the thing, but generally one slave. Why? Because I told you like I wanted to make my one module which works as a slave also, as a master also. If you can while instantiating it, you have to make some trick so that the same module can work as slave or master. That's why this thing. Otherwise, there is one more thing, clock in. This clock in is needed. If you are using it as a master, then this clock in will come from your CPU or microprocessor or your SoC. This is the reference clock from your system. And there is another SCLK. This clock is not used for the master. It is a reference to the slave. Now the same module, if I use it, if I want to use it as a slave, then I don't have a system clock. Then this clock in will become my SCLK in. Like I need a reference from my master. So then the SCLK of my master will be connected to clock in. That's how the same module can be used as a slave also. And there is two more signals, load and unload. Why? Because you are sending data from SPI protocol, SPI chip. So where this data comes from, it will come from somewhere, right? Generally this chip will be part of your SoC system. Like if you give it to me, I'll hook it up into a microprocessor or any other bigger thing where other things are happening and some data is generated. So that data will be loaded to this SPI protocol register. That internal register will be loaded. So when it will be loaded, when that data will be ready, so you need to tell your SPI protocol by some signal that, hey, load my data. This is the signal load. And also think about your slave. Slave receives the data. Then if the slave receives data, then what it does? It will use it, right? Who will use it? SPI is just a protocol. Then in slave's side also, there will be some other hardware which will use that data. So that hardware need to unload the data. So when it will unload, like when it will say that, then that signal will be used by that other hardware from the slave. And slave will say, okay, I am ready to give you data. This is unload. And based on the unload signal, the other hardware will take the data. Then the data validity will be the data will be valid based on these two signals. So this is, we are saying that this is a chip, 4-pin chip, 5-pin chip, but actually it will be used with some other hardware. So you have to take care of that thing also. But specification says that only 4 pins. But see, when you go to implement it, you need more signals so that this protocol can work with other hardware also, which is present in your board or in your SoC. So just to make, like, I took this much time because to explain this thing. The moment you go and implement something and write your test bench, then all the other things uncovers, all the problems starts coming, all the things are uh, getting visible when you try to implement something and simulate. And that time your thought process also starts, then only you start learning. Otherwise there is no way. Everybody knows what is SPI protocol. You ask anybody, they will give you like tons of lectures, hours and hours. But the moment you try to implement it, and after implementing, if you want to hook it up to something like a camera, where what the camera will, what the camera needs, the data from SD card. It will read the data and give it to your MPEG decoder. MPEG decoder is another hardware that is present in camera. So MPEG decoder, then when you hook it up to MPEG chip with your SPI protocol, then you start to see, experience what are the problems, what are more signals are needed, how it can be coded, how it can be worked. Again, when you capture a picture, your MPEG has encoded it and given back to SPI protocol. Then it has to transfer the data to the SD card on the camera. Then your slave side of SD card, that needs to get the data and transfer to the flash memory. So how to hook it up, that slave with the flash controller? If you do those things, then only you get to see all the full picture, the bigger picture of the VLSI design or system design. Basically this comes into system design, total system design, when you try to do total system design. So try to hook it up, try to think in this way, and make it happen. So this is the design. I'll not go deep into it because the same SPI protocol can be coded in many ways. Just try it. What I wanted to do. Yes. So whenever your this is called design. So generally, I use generally Verilog. iVerilog is a simulator that is open source. I use it, and it is pretty much enough for me. And I have done the chip manufacturing also. So believe me, you don't need Cadence, Synopsys, anything else, any other simulator fancy things. This try to work. This is little bit like old fashioned, because this is in a window, there is no GUI, nice pictures, nothing. But please try to use this, try to get accustomed. This is a very nice tool, and you will love it. And this is very simple. I will compile by using iVerilog. When you save your code is working. See, there is no errors. That means your design is fine. So, but this design, if you want to simulate, it will not simulate because the input output we have not added, we have not forced any values. So nothing will come. So if you do, there is a new a.out file is created. If you simulate means a.out running a.out, it will give nothing. So that's why you have to use something called test bench. What is a test bench? See, this is called test bench. So test bench doesn't have any input output, because you can think about it is a kind of PCB where you have put your SPI protocol, and you have to give the battery the other input signals or something like that. And this is how you do it. Um, and here is the this thing, you drive the signal, you are now adding the values. RS means the reset things, control in, data in, blah blah blah. You want to drive and see whether in all possible cases that you can think of, the hardware is, the code, the verilog code is working fine or not. So this is how test bench is written. And this is another trick. VCD dump, like dollar dump file, you use one dump file name, and dump vars 0 comma test bench. Just search in Google, you will get it. How to dump VCD. VCD means value change dump. So whatever you are simulating, I'll show you today. I'll show you that you can visualize in a waveform viewer. So this is how you create VCD file. And this is how you instantiate your chip. So this is something different. This is how you create a clock in your test bench. So every 10 time unit, clock becomes not off clock. That means it will give you a time period of 20. And at the beginning, if you make it like 1 nanosecond, that means it will be a 20 nanosecond time period. That means 50 megahertz. For RTL simulation, the timing doesn't matter that much. You can do whatever clock signal frequency, that really doesn't matter. So I wanted to show you some other test bench. VITB master slab. If you are not clear, if you can't see the this thing, just let me know. So here, this is the master slave configuration of SPI protocol. Still not. Now it has come. See, this is a master configuration, the same slave. So though I have designed only one master, and the way I have designed it can be used both of them. But in test bench, what I wanted to show, that in test bench you have to use both master and slave for most of the protocols, because protocols, if you are targeting any protocols, means there will be a sender side, there will be a receiver side. So to test your sender side, you need a receiver side in test bench also. So just make sure of that. So this is all about master slave. I can simulate it. Let me try to simulate one of this thing. Test bench. See, this is simulation. Now you are getting output. Why you are getting output? Because I had written. See this dollar display dollar monitor, because of these statements is printing out this thing, otherwise you'll not get it. So these are also very important for your, this doesn't add to anything to your design, but this add to lot of value to your verification. This is very basically the very basics or very primitive kind of verification. So I am adding data in, then clock in something something, and I get some output, and I check. I know what it should come, how it should come, when it should come, and I'm verifying all the time stamps like that. And there is another thing I have to do while compiling. Uh, I have to basically make a this thing minus capital D. So if I use this switch, then and then I run this thing, then see VCD dump file open. This is written. So if you see, if I do ls spi.vcd is kind of generated. So now if we have this um, VCD file, then you can load it in GTK web. What is GTK web? You will see it right now. So this is your design, and you can load it like this. See, this is the clock. It is pulsing. It is showing here control, some control signal I am putting, and RS reset signal, how it is there. All this thing visually you can see the waveform, and it is very good, very easy to find your problems in your design, because here you can have like marker each time, like when clock is one, this value is this is the value, and you can check, you know what time it should be, what that you have to have this mind, and this gives you a very good verification of your design. So these are the three things basically you have to do. You have to create your own design, keep it in a .b file, then you write your test bench, instantiate the test bench, your design inside the test bench. If you have a master slave configuration, do it, and then write the test bench very thoroughly. Most of the things, most possible ways of using your hardware, that you have to do it in a test bench. If it becomes very big, then write 3 4 5 test benches, and compile that test bench, and you simulate and see the simulation result in GTK web in web form. So that's how you can do the verification very well. So this is the common thing for all the protocols, not only the SPI things. Okay, but since it is the first thing I was discussing, I took the opportunity to show you the full work that you have to do for sure. Any questions so far?
Alok, I have one question.
Yeah.
How, when you're using ivory log, simulating using ivory log, how do you specify the duration of simulation?
So that's what I told. Like simulation,
Hmm.
the time scale, the unit, nanosecond, picosecond, it
Oh,
doesn't matter.
okay, okay.
But still, if you see, uh, because it is all in fictitious time,
Hmm.
but still, if you want to specify something, there is this directive tick time scale. 1 nanosecond is the thing, and 1 picosecond is the precision. Like in 1 picosecond steps, the simulation will happen, the smaller step. And the bigger steps, like #10 means 1 nanosecond means it will be 10 nanoseconds.
No, okay. Actually, my question was like, can you go back to that simulation which showed that numbers there?
Oh, okay.
Yeah, here it's the timestamp shows that 270 nanoseconds, right? There in the simulation which you just ran.
Correct.
So, for example, here it shows 0 seconds to 420 nanoseconds.
Ha.
So, how
Correct,
do you
correct.
specify that duration? Or
Oh,
how
okay.
long? Yeah.
So,
Even when you ran that GT is not GTK wave, that ivory log,
ha,
stopped at 270 nanoseconds, right?
okay, okay. Correct.
Yeah.
See this finish, it will tell you. So you have to add like this from 0, this is 10.
Okay. Okay.
10 plus 30, 40, 45, 50,
Okay.
50 plus 50, 100, 120, 140, then 290, like that. And after this line, it will again, like still it will simulate for 300 more time units,
Yeah.
then it will stop.
Okay. Okay.
And sometimes it finishes, like stops automatically, but sometimes if it goes into loop, then it will continue, like it will hang. So that's why I use that dollar finish, means whatever
Okay.
happens after that, the simulation will for sure stop.
Okay. Okay. Thank you.
So if there are no more questions, then I'll go to the next protocol, which is I2C. I2C was invented by Philips, and I think all the display things, LCD, small, like 2 row, 1 row display, that is used by the projects, by the students. Those small LCDs, LEDs, those are all communicated through I2C protocol. And Philips used it for its television, and inside their chip, they used it for all the peripheral devices. They used to use it. So I2C is kind of, what should I say? Uh, Only 2-pin protocol. SPI has 4-pin, and if you want to address more slaves, then number of pins increases, 4, 5, 6, but basically minimum 4. Here only 2 pins. One is SDA pin, one is SCL. What is SDA? SDA is the data where the data transfer happens, and SCL is the clock reference. Here also master slave configuration is allowed, and master gives the clock reference. Here also the reference is clock reference is shared between master and slave. And SDA is the data, only one. So as you like, it's a common sense, right? So since it is one line, either data can come from master to slave or slave to master. But if you see, if you remember the SPI protocol, there was 2 different pins, MOSI, MISO. So that is called full duplex, means when data is coming from master to slave, at the same time data can go from slave to master. So time is not wasted. Nobody is waiting. So full duplex, but here it is not possible. If the data direction is from master to slave, then slave to master is not possible, and vice versa. So it will be a little bit slower, but easier, less number of pins. And also see, there is no chip select thing. So basically, then you cannot address which slave you are sending the data, right? So there is no way to tell that, okay, I want to send data to that slave only. Master cannot say that. So that's how it is like kind of throwing things in the air, right? In temples, sometimes you will see they throw the money or coins in the air. Whoever gets it, like that. This protocol is like that. So master can broadcast. This kind of thing is called broadcasting. It sends the data, and slaves, all the slaves can get the data. So that creates some kind of problem. Like, this data is for which slave? So that is addressed by the right picture, which is basically a protocol. Like protocol means what? A system, a rule kind of thing. So here it says, like, when the data from master to slave will start with a start bit, start condition. It is 0. Then 7 or 10 bits will be address frame. So frame, you don't know, like, you cannot do anything frame or something. The data will come as 0 and 0 1, like that. In one line, it can be up and down of that signal, nothing like that. But this thing you have to implement in your design, in your Verilog code. Like, you have to take the first 7 or 10, that you have to make sure, like, you will use only 7-bit or 8-bit. So after the first bit, if you see this is 1 or sorry 0, then you say that, okay, now transmission is happening. Then you take what you call, if it is not start bit, then you ignore what is coming. If it is start bit, then you give the value importance of the next 7 bits. When it comes, store it in a register, then decode it. What is that value? That will be a number, like 7 bit means to 128 numbers can be there. So one of this number, whatever and you have to number your slave 1 0 1 2 127. So if whatever that number is, means that this message or this data is for that slave. So internally, each slave will decode that 7-bit value, and it knows what is my value. If it matches, then only after 7 bits, whatever the rest of the things, like from here to here, it will accept. Otherwise, if this doesn't match to its address, then it will discard, it will do nothing, it will not, ignore all this thing. Whenever this value matches to its own value, then only it will accept next bits, and then see the value, read or write. Whether read means it has to accept the value from master, or if it is write, then it has to send the value like that. All these things happens after that. Then after this read or write happens, then acknowledgement has to be given. If it is a write, then it has to say that, okay, I have got the data, fine. Then master says, okay, the transmission happened successfully. All these things, the handshaking, some intelligence is built into this protocol. So this picture is very important for I2C. And why this is important? Because of that thing, two line. There is no way to distinguish things. And this, why this is little bit like better protocol than SPI, because it has all these values: read, write, acknowledge, then data frame 1, again acknowledge, data frame 2, like that, acknowledge, and it can happen like that. So 8-bit. So essentially, the main data is in this 8-bit. So series of 8-bit will come with after with an interval of acknowledge. So after each 8-bit, the slave can send, okay, it is received correctly or not. Master can get an acknowledgement like, okay, the data transfer is happening. So that check was not present in SPI. But however, this webinar is not to show the difference between protocols, just a discussion, and it is everywhere in the internet. Don't worry about it. Even if you cannot follow today, it's fine. It's everywhere, all over the internet. It's a very old protocol, but still it is used in Philips, all the hardware. So just get these things and try to implement the basic things. So similarly, these pictures, like since I have to present something, I have collected so that my slides doesn't look empty. That is the reason. This is again available. And again, this is the data. And this is the clock reference, very important. See, this is the clock reference. So each clock at this edge, what is the value of this line? 0. That means it will accept the first bit as 0. Again, one is the rising edge. This is the rising edge of the clock. What is the value of this? This is 1. Then 0, 1, it will register. Like that, each rising edge, what is the value of this line? That will form the data actually. If this clock signal becomes like slower, means bigger, then if it is same, the same waveform will be decoded differently, because the age is coming differently. Whenever the age comes, only that time it will be sampled. So if the age comes different time, or less frequently or more frequently, the same waveform of SDA line can be decoded differently. And this is true for SPI protocol also, all the serial communication. Because serial communication means only one line. And there should be some reason and some ways to tell that when to sample the data line. So this is true for everything. So that you have to understand very clearly. And master slave configuration, this is the master and multiple slaves. So when the data is sent from master, it goes to everywhere. That's what I was saying, broadcasting. Then from these first 7 to 8 bits, it will check, it will compare with its own address. If it is matches, then it will accept this rest of the bits or ignore it, like that. Since there is no chip select or something, so multiple master is possible in this protocol. See, there could be multiple master, multiple these things, and this is connected like this. See, I must tell you, in picture this is very simple, but in design this is very difficult. This is called bus architecture. Bus means in one file. See, broadcasting is easy. Like this is output. Output can go to multiple inputs, no issues. But see, if it is output, if it is output, two outputs cannot be shorted like this. This is saying that simple copper wire is connected. Two output is connected together. In bus, actually this is connected like that, but there is some catch. So suppose this gives you 0. From this master, 0 value is coming out, and this master 1 value is coming out in one line. So 0 1 means it will become short, and the whole circuit, this and this, will be short circuited. This is VCC to VSS grounded. It will be short circuit. That is called bus like contention. That the specific term is bus contention, because you connect two output things like this. So to overcome this, there is something called buff-if gate, buff-if not gate, like that. So that looks like a NOT gate or buffer, but with a control pin, and that control pin has to be driven properly. If every whoever is driving, like connected to bus, means potentially they can drive the bus. Whoever is driving the bus, it has to take the control of the bus. Then the control signal from that unit should go to the control signal of those buff-if gates. Otherwise, if you see the truth table of buff-if gate, if the control is 0, the output is high Z, means high impedance. And if the buff-if gate is input, that control input is 1, then from input to output, the value propagates. So that high Z things, that is very important. That means it is not taking control of the bus. And if it is high Z, means high impedance. High impedance means high reactance, resistance, whatever you say. If the line is high impedance, then other hardware can write value into that will not create a bus contention. So designing this line also kind of tricky, and you have to take care of that thing in your code. And that I can show how to do that. Basically, there is a ternary operator, colon, question mark, colon. So the control signal should be the first, then question mark, then the input signal. Then after colon, you have to tell IZ, like 8 tick H, Z, 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 like that. So that's how you can implement in RTL the bus architecture. It is simple, 1 line, 2 lines of code, but you have to know, you have to keep in mind. So essentially, multiple master, multiple slaves are allowed in I2C protocol. Anybody, any questions? So lot of things has to be taken care. That's why I am not giving you difficult design, because unless you start designing something, those who are designing for the first time in your life, start very simple, still you will face so many problems when you try to make it work by yourself. And we are trying to manufacture it. So it is not like your project or something. If you even if you copy, I am telling you rightly, even if you copy, because I'm opening it, like, take it from the internet, wherever you are taking it. The moment you try to make it, simulate it, try to make it, you will have a lot of problems, and we are going to manufacture it. And if you do copy paste, it will definitely not work. So the next, very old, very old, like very, this is the backbone. This was the backbone of industrial automation. Universal asynchronous receiver transmitter. So why this was backbone? Let me tell you. Let me explain the protocol first. Um, this is also two pin, and this is full duplex. Why? There is a transmit line, there is a receive line. So both the data transfer from one device to a master to slave, slave to master can happen simultaneously. That means there is no waiting time, no loss of time. So it is full duplex. But see, there is no clock reference. So that is the difference. So this, that is why it was the first, I think, serial protocol. Or I think RS-232 was the first, and this is a little bit of modified version of RS-232. RS-232 also is the same, or I think RS-232 is only half duplex, something like that. And both of them doesn't have any clock reference. Why? Because in other SPI or I2C, what I'm saying is, like, the scope of the design is like a PCB within a television, within my camera or SD card, something. The data will travel very small, millimeter or some few centimeters, like that. But in industrial automation, it can travel, the data can travel like meters, kilometers, even 100 meters, like that, from one plant to other plant, like that. And if you know, like, transmitting signal over a long line, the transmission line theory comes into play. The impedance matching, blah blah blah, and associated, like, a long wire can act as a high capacitance, high inductance also. And generally, clock is very fast moving, like high changing thing, right? So high low at a regular, very fast interval. Even if that time it was like 1 megahertz or 100 kilohertz, like that, but still it is highly thing. And over after few centimeters, because of the high capacitance, the maintaining clock at high rate was not possible because of those crosstalk issues. Those are all those things together called crosstalk. Like capacitance, resistance, reactance, inductance, all together called. So that is why after a long wear, at the end of the wear, rising a signal, it's difficult, because you have to drive a lot of capacitance. Means you have to feed lot of charge. Rise means what? You are charging a capacitor and you need lot of power. So that, because of that thing, fast moving signals like clock was not possible. That's why only data line used to be there, because data, it would potentially change like clock, but very unlikely. Like generally it doesn't happen like that, but still data can travel long, because it has time to settle. Maybe after few like microsecond also, if the rise fall is slow, still it can be detected at the other end. So that was the reason the clock was not given to this protocol, because it was not feasible. But keeping those aside, so the protocol is one start bit. If the first bit is 1, then you can take the next 5 to 8 bits, add data. After that, 1 parity bits, or 1 or 2. I think 2 is not used. 1 bit stop bits. Stop bits is generally 1. Start bit is generally 0. So this is how the protocol works, and parity is not mandatory. You may implement, may not implement, like that. But again, you may say that then this bit means what? There is no clock reference, right? This guy is sending data, means it has definitely some internal clock. Based on that clock, it is sampling data and shifting the registers. Data is coming out, but that clock is not available here. This is sitting maybe 100 meters away, and you are not giving the clock from here to here. Then how it will know that it's one also here? Because everything data means only the edge of the clock, and if the two devices, the clock frequency is not same between the two devices, the data will like for sure it will be corrupted, right? Even if the phase is not right, whenever the rising edge of this guy, the same time the rising edge should happen. If there is a phase mismatch also, the data will be received that is not valid. So how can you make sure that? That's why there is some concept of baud rate. So baud rate is some kind of some concept of clock. It is not exactly clock. How many data samples per second, like that, like that. Just think, read through the websites. Find it very popular thing. And those who are little bit grown up guys, if you remember, we used to have a modem for internet. That modem used to be connected to the telephone line with RJ45 plug, and there the modem we used to send the baud rate, and that baud rate has to be matched by the BSNL server. That means that's whenever they used to give connection, they used to say that we will be sending data in 15,000 baud rate. Then our modem has to be set at 15,000 only. Then only the communication, the handshaking will be proper. Otherwise, whatever data will be received by modem, something will be received that is not a valid data. And we didn't used to get right website, or internet was not connected, like there are a lot of problems. And sometimes we on our own we used to change baud rates, like okay, it is not working, let's see 4,800 baud rate whether it is working or not. So those kind of things, some sense of some concept of a clock, that is baud rate. Just think, like read through it, and you have to implement baud rate to implement UART. This universal asynchronous receiver transmitter means UART. So you have to implement baud rate for both sender and receiver. Generally, master slave generally not used in this thing, and because there is no clock reference, anybody can send any data anytime. Those kind of things are not there, basically, like address of slave, comparing those things. It is just sending data, but nothing more complicated. So this is the protocol. This is the topology, and this is some kind of example. Start bit 0. Then you will be sending the data frame. Then parity. If you are sending parity, then you can implement. You cannot implement. So, but you have to know whether this guy is sending with parity or not, because if it is not sending parity but this guy is assuming that the 10th bit will be parity, then it will receive invalid data. So that thing has to be understood. Some many things here is not evident through signals. Some things like baud rate, parity bit, all these things has to be known between two devices. Then only you can configure and you can do this thing. So just keep this in mind. And basically, this is the transmission. Only data goes, and based on the baud rate, it sends. Based on the baud rate, it samples the data. Similarly, this side will have a TX, and this side will also have a RX, and they can, like independent of this line, they can also communicate to each other. And this is how it will be received. Questions? Okay. If no more questions, then let me show you pulse width modulation. Pulse width modulation is a circuit, very simple but very effective. So it is used for audio. Some buzzers and all those things are used by this thing. PWM audio, very old computer used to have PWM, and you can with PWM you can play songs also, like old primitive kind of data file that used to be there. And sound card, old sound card computer motherboard used to have PWM for sounds. But the major application of PWM is into the motor control, and also motor control and lighting, the second most important thing. So the thing is, motor generally we give current or voltage and it runs, like it turns like at high speed, RPM, 1000 RPM, 200 RPM, whatever. But there are some motors that is called servo motors, which doesn't turn full. We don't need the full turn also. Like one turn also we don't need. Where in robotics, arm, right? We don't want in the joints of hand or leg or whatever. We don't need the hand to rotate like 200 revolution per minute. No, we want hand movement which is only in angular movement, 30-degree, 20-degree, 15-degree, so that hand is moving. And there also there exists a motor for that movement, but we don't want that motor to turn even one full turn also. We always need a angular displacement there, 5-degree, 10-degree, based on the whatever decision you want to move that hand like that. Also in heavy earth, like JCB, or earth moving equipments, also very powerful, high power, where digging holes, digging roads, all those are servo motor control. And there also we don't need full turn. We need that JCB hand to move some angular movement. So there, how to control the angular movement of a motor? That motor is also constructed differently, so that it can. So this is called time period of a signal from 0 to high, then 0, then again before going high, from this to this. This is called time period. And most of the cases in digital electronics, it's in a square wave. This is the like generally we get a signal which is 50% time up means 50% it is down, and this is called 50% duty cycle. Half of the time it is up and half of the time is low. If you give this signal which is 50%, then servo motors generally don't move at all. To move it, you have to change this uptime and downtime. So this is a example of changing the duty cycle. See, very small time it is up, then little bit more time it is up, then little bit more, like that. So this is called pulse width modulation. So we are not changing the frequency, means time period remains same. 0 to next 0, this time period remains same, but the amount of time it is high or low, that changes. That is called pulse width modulation. So based on this thing, if you do this thing, suppose if you do this, the signal is giving 10% duty cycle, means 10% of the uh, time it is up, then it might move 10 degree. If you give 20% of duty cycle, then the motor will like move 20 degree. For example, actually it could be different, but the idea is based on the uptime, the angular movement can be different. Say the one more thing you can understand very easily. Suppose if your uptime is less, means this signal is one very less time. That means this signal cannot give more power. Like it is less time it is up means one high voltage 5 volt or 3.3 volt, so it is up for very less time. So average, if you average out over a time, the average power delivered by this signal is less if the duty cycle is less. Understood? So if you send this signal to any bulb, so bulb will glow only 10% and it will be off 90%. A human eye, how we will perceive it, we will see that bulb is dim. It is not glowing to full power. But actually what happens? 10% time it is glowing at full power, 90% it is off. Since our eye cannot detect that thing, it is happening very fast at maybe 50 megahertz rate, we will like perceive it as the bulb is dim. So in theater, in photography, or wherever there is a dimming of light is needed, this is another technique used by pulse width modulators. So LED dimming. Nowadays, LED dimming is the main thing, very, very prominent user of PWM is LED dimming. So this is the use of PWM. And it is very small Verilog code. I can show you. I have a code. So this is I am using in my SOC, which I will be manufacturing very soon. Because if you see nowadays, all the students who does like projects, in college. There will be competitions by IEEE and colleges or many things. What do you do? Basically, you buy a Arduino, very bare minimum, Arduino Uno, and read the specification of that. This is like must. This PWM, one input will output will be PWM output. If you go to Arduino, other things after that Uno, little bit higher, and all those things, all those other protocols will be added. So design anything which Arduino has, we'll accept it for sure. So like that. So coming back to this thing, this is clock in, reset, chip select, uptime. See, this is the value uptime. How much time it is up? What it is 3-bit. I'm using 3-bit signal, and it will become. See, this is the range. It is becoming range, and it will show you it is connected to. See, uptime is connected to uptime latch. So this is a 3-bit latch, and 3-bit means it can have 8 values. So it can have 8 values. I can change the pulse width uh, 8 times, means 100% divided by 8. In the step of 12.5%, I can change that my PWM signal. If you make it 4-bit, that means it becomes 2 to the power 416. So 100 by 16 means 6.75%. In a step of 6.75%, you can change your PWM signal. So this value, this number of bits will tell you the resolution of your PWM circuit. So all this is available in internet. You have to read and design it. And there is a counter. It just counts from 0 to end of this counter and gives a signal. Whenever this counter is up, the some logic is there. Then clock out. See, this clock out signal I am deriving from uptime. So that's how I am modifying. So if I compile it, Iger log pwm.v, then testbench.v, a dot out. Okay, this is just a text file, and I have to do minus d dump underscore vcd. So now the vcd file is created, pwm.vcd. See this signal. So enable, whenever I enable it, so this uptime is latched based on this thing. This was first the uptime, then after this enable, uptime changes, the duty cycle changes here. Again there is a enable signal, after that uptime changes. See, so far I have not told you enable signal, PM out, uptime, whatever, blah blah blah. See, when I went to implement, I realized that there should be some enable signal. Otherwise, this value change, when I want to change the uptime, that uptime has to be synchronized with some signal. Then I had to add this enable signal. But in the discussion, there is nothing called enable. So just make note of that. Whenever you go to implement, then you might see you need more signals than the specification has. So that is one thing, very like interesting. So this is how my pulse width modulated signal looks like. Unless the enable signal is there, uptime doesn't changes. When uptime changes, then the pulse width changes, like that. So you have to do the same thing, similar thing. So this is pulse width modulator. We have covered. Any questions? Okay, let's go to the next one. And I should not give any introduction for this protocol. This is your monitor. Till today, I don't know whether you will agree with HPI, I2C, PWM or not, but you cannot deny that this protocol is still used today. This is the protocol that powered our desktop for last 60 years. It is being used since last 60 years. So this is also 5-pin protocol. RGB, red, green, blue, horizontal sync, vertical sync. Easily available in the internet. Just I have to show something, that's why I have this thing, but I'll try to explain a little bit. So display has many like it is complicated, but most of the websites it explains very well. So actual area, display area is this, which is generally called like 540p, 720p, 1080p. Means 720 means 720 pixel, the vertical size it is says, and based on the ratio, aspect ratio of display, if it is 16 by 9, that means if you divide 720 by 9, means it comes around 80. 80 into 16, that will be the value of the pixel in the horizontal direction. Similarly, 1080p means if you divide 1080 by 9, then you will get 120. 120 into 16, that will be this. But the display has areas beyond that also, till the bezel. And to make a frame, make a picture, you have to tell what is the color of this each pixel. Like if it is 720p, means 720 into 1260, that many pixels are there, means dot, that many dots. You have to tell what is the value of RGB of each of these dots. That is the trick of this protocol. And you have to tell that thing, and after that thing, see, this is the timing diagram. So this horizontal sync, first it has to be 0, then it has to be up for some time. In the specification it is written, and that is dependent on the display also, like 540, 720, based on that thing, what is the value of this signal, how much time it should be up, that will depend. Then it will go again low and it will remain low till this end, like that. Again it will go up like this. Similarly, vertical sync has also some protocol. It is 0, then high, then low, then again high, like that. So basically, essentially what is happening when you are trying to create a new frame, you have to do this vertical thing. Then during the horizontal sync, when it is low, then you draw each pixel, then you scan like this, one by one, each row you scan. And after that thing, when you scan, the vertical sync should be low, and then you finish the scanning all the rows, then vertical signal goes up. After that only the whole color or the picture, the value of the all the pixels will be shown here. So first this scan will happen, horizontal, all the scan will happen, then the vertical sync will go up, then only you will be able to see the picture here. That is how. So the question arises, how to create a picture, basically picture of person or scenery, or very like trees, greenery, anything. So that means each pixel will have different RGB value. But all those are very difficult. What you have to do, basically, take one value itself, or maybe 1 G, maybe 0 or something. See that thing, whatever values, keep that value for all the pixel. Then what you will see, based on that combination, you might see the whole screen as red, blue, magenta, yellow, orange. One color will come, no picture, nothing. Still that is fine. You are able to create something. Then when this horizontal is going like this, try to change the value of RGB also. Then maybe this pixel, for some region it will be red, then it will be blue, then it will be bar like that. That is another step. First try to keep RGB fixed for all the pixel, then try to change after regular interval, so that that bar. So remember, if you have a bad screen or something, you get bar color. So try to do that. Then after that, decode a JPEG picture and take the value of one JPEG picture. Means it'll give you the pixel RGB values or all the pixel. See if you can fit that thing here. Then you will see a picture really like that. So very interesting project. Try from very basic. First create these pins, protocol, RGB, and a fixed color. Then try to change that color, maybe the whole screen from blue to red, like that. Then make bar color, one region red, one region blue, one region, like that. Go in this step by step order. Very interesting project. Any questions? Okay, if there are no more questions, you can design memory, and memory can be analog. Mostly nowadays, the popular memories are analog devices. So you have to design 2T generally DRAM, 4T, 60, 80, 10T SRAMs are there, and generally sometimes non-volatile memories are also can be 2T, 4T, but those transistors are different. Those are floating gate transistors or Sonos transistors. So we don't support floating gate because of our technology, Global Foundry 180 nanometer. We support Sonos transistors. If you want to try and just search this thing, Sonos transistor, creating a non-volatile memory, means like a SD card kind of thing, and you just make sure don't make only one cell, because these Sonos transistors are very small, less than 1 square micrometer also. So make at least like 32 byte. 32 byte means 1 byte means 8 bit. So 32 row of 1 byte, or 64 byte, or 128 byte, like that. A product kind of thing. Manufacturing only one Sonos transistor is difficult, basically. So make a product 32 byte or something like that, or like this. Or the simplest thing is creating with flip flops. So these are synthesizable. So you can try that also, and this is very easy to create in code. So I have a DFF RAM. I can show you. This is 8 word of 16-bit word, 8 of 8 rows. So this is the thing. Basically, let me show you. Uh, See this module. This is basically a reg Q16, means it is a 16-bit register, and this is a 16-bit register like this, with a simple always block. This is one row of a memory, and the module name is memrow. Okay, so this creates one row of memory, and after that, see, I have instantiated 8 rows of memory, and there is some decoding, like address decoding and output decoding logic. So you can make it like that. This is called DFF RAM. Why? Because here we don't use transistors. We write like right away use the DFF. You know, DFF means D flip flop, which are used to store values. So they can be used, but generally they are not used. Why? Because a DFF cell is very large, like almost in our technology 180, it is almost 50 square micrometer, whereas a 60 RAM cell could be like 1 micrometer or 2 micrometer square. So very space saving technology. Those are things. And Sonos transistors are even slower, like smaller, and DRAMs like 1T, 2T cells are even smaller, like less than a square micrometer. So though they are actually used because of this thing, but these DFF RAMs are used as a register file inside microprocessors or wherever you need small amount of memory but very fast. These memories are very fast, so they can be used very close to microprocessor. Very access time is very fast. So you can create the memories also. If it is very easy to create a DFF RAM, and if you are creating that and verify very well all the read processes, write processes, and all those things, verify very well, and you can submit it. And if you want, um, like if you want to try 2T60 RAMs, SRAMs, That is also welcome, but this will come into analog domain. It is not digital, but DFF with flip-flop latches, it comes into digital circuit. With 2T, 4T, 6T, it comes into analog domain. And this thing, I don't know whether you will be able to design a floating gate. No, floating gate is not possible, but Sonos you can like target, but I'm not sure whether you'll be doing it. And microprocessor. Try from scratch, read a book, Hensi Patterson or Maurice Mano. They have shown how to create a basic microprocessor, but it takes time. 2 months will be very difficult, but if you already have designed microprocessors, if you have some kind of 8-bit, small is also fine for us. Don't think that you will be able to make i3, i5. It's not possible. So any 8-bit microprocessor is fine, because till today ST Microelectronics sells their product line STM8. That is their 8-bit microprocessor. So it sells in billions still today. So no need to think about 16-bit, even 64-bit, and 32-bit. 8-bit, 16-bit microprocessors are really good, because all this Arduino product line, they are either 8-bit or 16-bit. So let us create at least Arduino. The in Indians have never created 8-bit microprocessors. So let us take up baby steps, and let us do something, even if it is similar or easy or not complicated, still it is fine. So that's it. If and you can create the subsystem of microprocessor also. I'll be interested in other, for example, Mac instructions, like in DSP, multiply and accumulate in single cycle using pipelining technique. So that is also fine if you want to create a multiply and accumulate, that kind of instruction. Multimedia extended MMX subsystem, if you want to do like matrix multiplication, so that we can use it in GPU. That those kinds of subsystems are also okay. And like that. And another would be codecs, MP3 codecs, for example, MP4 for video, MP3 for audio. If you can design codecs, that is also very widely used. All the audio, video, television, and sound systems, they depends on audio and video codec. So those circuits are very well, we will welcome. So these are the some guidelines, that not guidelines, like some of the examples, some of the recommendations from this IEEE Fabulous we are giving you. But you are not limited to that. You can think something else also. No issues. But only one request, just to like just to like advertise yourself within your friend circle or industry, that I have done this big one but could not complete it. Better do small one, complete it. That would be really grateful. Okay. If you have any questions, just let me know. There will be another similar kind of uh, webinar next week, maybe. Some kind of this kind of advices, maybe someone will give you for analog IPs that you can target, like that. And please now start designing, and just email me. You have my email, and whether you are ready to design, submit. and we'll by before next week we will um, uh, like send you the links where to submit your design. But please make it ready. You parallelly you work. Only attending webinars will not help. You have to talk, because after next week we don't have anything to discuss unless you have some problem, and we can give you some solutions, suggestions like that. Next onwards, the webinars will be like that. If you have don't have anything to talk, then probably will not also have anything to talk. So like that, from next or next to next webinars, we will be discussing your designs only. Yeah, one question I got from, let me stop sharing. One question I got, email I got, that whether the participants will get certificate of or not. So actually, I mean, I don't know whether it matters or not. Even if you get a certificate, it doesn't mean anything. When it will mean for sure who will submit design, that means they are taking part in the contest. Still now, we are trying to explain, and still now nobody is in the contest, right? Now it's time to be part of the contest. Send your design. If you send your design, yes, you will get a certificate that you have taken part in this contest, you have submitted this and this design, like that. If you complete it, then you will get a completion certificate. If you win, like you are among the 10 designs, then you will get that certificate, like that. Only this is not a course. So a certificate of participation in the webinars or in the program probably will not be able to give, or that will not have any value. You will get a certificate only you submit a design. If you submit a design, then you will definitely get a certificate. Okay, the floor is open for questions.
Good evening, sir. I had a doubt.
Yeah, correct.
Actually, I'm interested to do a analog IP, but I don't have any experience and the knowledge regarding many different kinds of analog IP and what is the architecture or the schematic that I need to do and what are the different calibrations I need to follow. So, is it possible that I can get any guidance on that, or after the next week, can we get some more time before we explore and we submit our design idea for the proposal?
Yes, guidance, like if you don't have any kind of background, then it will be difficult to give any like any kind of like from scratch. But there, as Sarfaraz told last week, uh, um, go to that analog devices website, like where you downloaded Electric or LT Spice. There are numerous videos there. That is the right starting point. We want to see, we don't want to teach, we want to only like handhold. If you are taking steps but you are facing issues, then only will be able to help from scratch, because we have also our own work, offices, teaching, and
Yes,
all
sir.
those things. Really, really, people are busy. So you can ask your teachers if they can help. Otherwise, only who takes like few steps, we want to handhold them only.
Yes, sir. I have a little bit exposure to analog design. Uh, uh, I implemented in electric the inverter as well, and even in the unicast I had done an LDO design, but I couldn't submit it completely because of it had mixed signal. It was a mixed signal SOC. So I do have a,
Mhm.
exposure, but I just wanted a little more clarity on pure analog design IP, which is also industry relevant.
Yeah, so in that case, we can help. I think next week we'll tell you what are the most important. Like I can tell right now also, ADC, DAC, very much we need it. Very much we need it. Then RAM, we already any memory and analog domain. I told today you can do it. You can try that. And 2T 60, it is very available everywhere. It is available. You can try to do it, and you can try to do layout also. Then if you have some layouts, you are getting some DRCs, then probably we can help. Like, okay, do this, then your DRC will go away. Like that, it can happen. And
Yeah.
if you
So
want, yeah, please go
yes,
ahead.
sir. Alok, sir. Yeah. So sorry for interruption. Actually, yeah. So I suppose, Daksh, what you are trying to ask is, like, you want an analog IP, like you want to design an analog IP, right? So for that one, like, you are already aware of the tools that you can use.
Yes, sir. Yes, sir. Yes, sir.
Okay. So if you are already aware of the tools that you are going to use, now what you can do is that you can look for analog IPs. Now, last time I explained what is analog IP, digital IP. Okay, and there was like ADCs basically, and in that ADC, like ADC means it will be having both the analog and the digital blocks. And if you're going for only the analog part, then you can go for the LNA basically, low noise amplifier. And there is one more that you can go for design, that is a CMOS sensor, like sensing circuit. Okay, so these are the two things you can touch. Like if you want to do like everything on analog, like you, if you think that you have to design the complete analog circuit, then you can go for these two, like LNA, or otherwise you can go for the CMOS sensing circuit. And there are some voltage regulators also, so you can work on that part as well. So there is a bootstrap switching is there. Okay, so those things you can work on if you want to like work on analog. And here, like we are not expecting that you will have a novel idea or something, but you can have an existing idea. But with that existing idea, you can just mold it a little bit. Let's say, because see, in GF 180, and the person who has already done, let's say for example, an op amp circuit. So if I do the designing for an op amp circuit, so I should have some specifications, correct? So I should have a proper, like what is the gain that is required. So it all depends upon the applications to which we are applying. So your design should be application oriented. Okay, so you should have like specifications should be meant for that application only. So LNAs can be of different types, but the specification will completely depend upon the application where you want to implement it and how you're going to implement it. So based on that one, you have to choose a specification. Okay, so designs can be similar, but the values will differ. And there may be, let's say for example, you want a higher gain. So if you want a higher gain, so you may feel like if you add a transistor, okay, so this could increase the gain. Or if you increase one more stage, it could increase the gain. So for that kind of a thing, you can just add a little bit of, let's say, one transistor, or you can add another stage. So like that you can come up with a design. But first of all, you need to know about for what application you are trying to build it, and what should be the specification, and target only the small analog blocks. And that is nothing but an IP design only. So IP is nothing but intellectual property basically. Okay, so intellectual property means it is already there. Okay, so it's already existing. Or otherwise, if you are getting some novel idea, so it will be your intellectual property, means it will be completely your IP. Okay, so for like making your own IP means you have to have a particular specification, then it will be called as your IP. So I think it clears all your doubts.
Yes, sir. Yes, sir. Understood. Thank you so much. I needed this.
Okay, okay. So we will mentor you means we'll just guide you. Like suppose for example you took up a specification and you started designing it. So if you face anything like any challenges like how to implement, or let's say for example, see what we can tell you is for example you don't know like what are the simulations that is required for fabrication. So we can tell you that okay, so you do these simulations, then only your design will be valid. So for that kind of mentoring we can do, but we can't give let's say because there will be a lot of participants, so we can't tell each of the participants okay you do this you do that, and for example how to design it, what are the parameters you should take. So those things we can't tell, but because that will take a lot of time, and for each individual it will take a lot more time. But yes, of course we can tell you that what are the simulations required. Okay, for fabrication what are the simulations required, and what are the values or nearby values if you get, then your fabrication can be successful. Okay, so those things we can tell you. Now for example, let's say you are taking a resistance in your circuit. Now if you take a resistance in your circuit and you do the simulation, so whatever results you are getting, so that will vary when you do the fabrication. Now when you do the fabrication, your resistance changes by 1/4 of that value, or in some cases like based on the technology it varies around 1/10 of the value. So there these variations are there. So for these kind of variations we'll tell you that you do this variation analysis, you do this process analysis, and then whatever output you're getting, that we can validate that okay, so this much you can achieve if you do the fabrication. So that way we can help you out.
Understood, sir. Thank you so much.
Okay, okay, okay. So Alok sir, you can continue sir. Yeah.
Yes, so that is the thing. And first of all, you think through it and submit your proposal, your project, and we'll take it forward from there. This is for everyone. So if there are no more questions, then we can call it a day. Okay. Okay. Thanks for having